Hello and welcome student to the today's lecture. So this is course number MA412 linear algebra, and today's lecture number 25. Okay. So now recall the last class we discussed about orthogonal set, orthonormal set, okay, and the orthonormal basis. But the fundamental question what is there, so one can ask that does every finite dimensional, for example, we are considering on this finite dimensional vector space vector space consists of a or content or has whatever, yeah, orthonormal rather orthonormal basis. Okay, obviously we know that every finite vector space has a basis, rather it is true for every vector space as a basis. Okay, but whether it is orthonormal or not, I don't know, right? This is another question to ask. And so let me just do it a toy case, try to understand that, and then we will go for the general case. Okay, so what happened, suppose we have a two-dimensional vector space, for example R2, okay, and this is my R2 plane, okay, and I have say two vectors, this and for example this, okay. So let me write down, this is W1 and W2, two vectors which are linearly independent, and obviously in R2 any two vectors who are not collinear, they are linearly independent, right? Otherwise, if they are linearly independent, means one will be a multiple of another one, right? So these two vectors are linearly independent vectors, but the thing is that they are not orthogonal, right? See, to check orthonormal thing, we need to first check orthogonal thing. Then we can obviously, once we have the orthogonal basis, then we can normalize it by dividing its norm, right? So only thing, the important thing is how to find out the orthogonal set which will be spanning the same thing. So what does that mean? That means so this is clear that this R2 is generated by these two vectors. They are linearly independent, right? Over R, okay, over R I should say, okay, not over Q, okay. And now can we find out another set that contains two vectors? Also this generate the same vector space R2, but the condition is that they are orthogonal. Now once we will have orthogonal, we can easily do it orthogonality, right? Now what we can do, so we need to, so for example, let me assume that this is my one vector, say v1, w1, and then I want to find out another vector which is perpendicular to v1 or w1, whatever. So the natural choice will be, this is the natural choice, this vector, okay, because this vector is perpendicular, right? So what you can do, suppose this is my vector v2, and then you can see that v1 and v2 are perpendicular, and obviously once they are orthogonal, they are linearly independent. That is already proved in our last lecture, right? Now how do we find out this v2 vector? This is the question, right? How do we find out? Now see that that law of addition of vectors tells you that if you add this vector and then this vector, then the result will be w2, right? So this is whatever the vector with adding v2 will gives you w2. Now what is this vector? So this vector is has the same direction with w1, right? So this will be some multiple of w1. So maybe let me write down some cw1. Okay, C can be obviously less than 1 also. In this case, C is less than 1. It can be bigger than, it can be the case that this vector is bigger than W1, then C will be bigger than 1, right? In kind of, I am talking about the length of the vector, or rather norm. Here we should solve the norm, right? So now it is clear that these vectors, we add those things, they will have W2. So it's clear that W2 is nothing but addition of V2 plus CW1. Okay, and hence you can find out V2 in terms of W2 minus CW1, right? But again, we don't know what is C1, C, like how does C look like. Okay, we just know that there will be some C of this form, right? Now that we can find out using the property of orthogonal set. So we assume that this V1 and V2 is an orthogonal set, right? So what does that mean? That means the inner product of V1 and V2, that has to be 0. But V1 is W1 and V2 is what? V2 is W2 minus C W1. So W2 minus C W1. Okay. I think it is better to do the other way. It is much better. Okay. So I should say that. Then you will have. So this is general. In general, we use this fact. But over R, it is not a problem. Over R, both are same. Okay. So let me use this fact that W2 minus C W1 minus W1, that is 0, right? So I use that property of inner product that tells you that this is W2 minus W1, and then W1 minus CW1 W1. This function is 0, right? But the C will come outside, and hence you'll have C times norm of W1 squared, right? Because W1 in a product W1 is nothing but the norm of W1 squared. So this is equal to this inner product of W2 with W1. Okay, and hence that coefficient C1 is nothing but the scalar C1 is nothing but inner product of W2 with W1, and then divided by norm of W1. Okay, so this is the method that gives you that. So what is the final vector? So finally check that you W1 comma W2 minus, right? So W2 minus C1 is what? C1 is this inner product of W2 with W1 divided by norm of W1 square into W1. So these two vectors actually are orthogonal by the construction or the proof. Okay, and they are not only orthogonal. I mean, once they are orthogonal, they are also linearly independent. Hence, they span. This spans, or rather this set spans R2 over R, right? And then once you have this orthogonal set, you can talk about orthonormal things, and that is you have to just so the V1 is W1 and V2 is this W2 minus inner product of W2 W1 divided by norm of W1. So this is the coefficient into W1, right? So now you can divide by V1 divided by norm of V1, and hence this vector will be norm 1. Similarly, V2 divided by norm of V2. So this will be an orthonormal basis. So is an orthonormal basis of R2, right? So this is the toy case. Now in general also this method is true for any finite vector space. and this process is called Gram-Schmidt orthogonalization process. So let me write it down. Gram-Schmidt orthogonalization process. What? So what does this process say? That if you have a find us an inner product space. So let me write down. It's a theorem. So let V be yeah. So I don't need finite here. So rather I should. So this is, you can start with any finite linear independent set and make it a orthogonal set. So let me just write down be an inner product space in general, inner product space. Okay, and you start with a set, say. So let me write down, say, W or some whatever. So this is yeah. So this is something, say, W1, something, say, Wn, be a linearly independent, linearly independent subset of V. Suppose W is subset of V, which is linearly independent, right? And then question is that can you find another subset which will be orthogonal subset of V. But interesting thing is that the subspace spanned by the W and the another set will be same. So then there exists some W dash. So the elements are of the forms of V1, V2, Vn. This which is an orthogonal subset of V, such that, what is the most interesting thing, such that their span is same, so such that span of W is equal to span of W dash. So what does that mean? That means you convert the linear independent set to orthogonal set, and the span is a subspace of the full process V. So W will be the basis, given basis, and you convert into a orthogonal basis of the subspace. Okay, they are same. This is the interesting fact. Okay, and not only that, you can actually tell what are these V1, V2, Vn, and now you note that the way we have done from the baby toy case, similar method we are going to use it. Okay, and okay, so now proof. So obviously the intuition tells you that you should do this kind of proof by induction, right? So we will use a mathematical induction in on this cardinality. So on n is the cardinality of W, right? Okay. Now, obvious, the first one is obvious when n equal to 1. So if n equal to 1 and linearly independent means that means the only vector is non-zero, right? Even 1, then obviously W1 not equal to 0, otherwise it is linear dependent. Then and consider W dash equal to that V1 which is equal to W1. So you choose V1 equal to W1 itself. And so that will tell you that this is orthogonal. Singleton element is also orthogonal. So this is trivial, right? And not only that, they span the same vector. So this is the same vector, right? This is obvious, n equal to 1 case, right? Now, induction hypothesis tells you what? So you consider or assume that. So assume that the statement is true for k minus 1, some number that is given, let's say. So let me write down the symbol W k minus 1, which is this is W1 to W k minus 1. There exists Wk and there exists Wk minus 1 dash, which will be kind of V1, V2, Vk minus 1, okay, such that both Wk minus 1 is orthogonal and they span the same thing. So Wk minus 1 and span of W dash same. Okay. So this is true for k, and then we will do it for k plus 1. Okay. So what we will do? So for k, so now consider the case for k. Now consider that Wk, so which is for the case of k. So this W1, W2, Wk linearly independent and define. Okay, so we define W k dash, and how do we define W k dash? So this is V1, V2, Vk by what? So your V1 is W1, and other than V1 you define any so any element. So write down, say, okay, so let me write down the k vector first. This is true for any k. So for any k, so k equal to 1, 2, whatever n. Okay, and for any k you define this is by Wk minus inner product of Wk and then Vi divided by norm of Vi square into Vi, and I equal to 1 to k minus 1, because till k minus 1 we know, and then we define for k. So 1 to k minus 1. So this is the main definition. This is for k equal to 2, 3. Okay. So for k equal to 2, you see that it is nothing but W2 minus inner product of W2 minus V1, which is also W1, and then this one. And this is exactly same what we did here. See, in general, this toy case. Okay, exactly W2 minus the product of W2 with W1 divided by norm W1 whole square. Okay, so this is norm into W1. Okay, so this is the definition of VK, and now we will check that these VKs are actually linear. Not only, I mean, they are actually orthogonal. Okay, and they are orthogonal, so they fulfill the condition, and not only that, they also span everything, right? So inner subgroup tells you that till k minus 1 they satisfy the condition that they are orthogonal, and also they span the same vector space till k minus 1, right? So let's first prove that they are orthogonal, then the rest thing will be easy. So you see that you start with Vk with any Vj, and you check that this is nothing but by definition. So what was Vk? This Wk minus summation I equal to 1 to k minus 1 inner product of Wk minus comma Vi with the norm of Vi square into Vi, right? And then with Vj. Okay, so for any j, so I am not taking particular j, it can be any j. Okay, 1 to n. Now for any j, then you property inner product that tells you that this is nothing but Wk comma Vj, and then the inner product and sum they comes outside, so this will be sum over I equal to 1 to k minus 1, and then this should be scalar, right? Scalar quantity, so that comes outside also, so I must write down. Okay, so let me write down one more line. So Wk comma Vi norm of Vi square into Vi and Vj, right? Now this scalar quantity come outside, and then you will get Wk minus V inner product of Vj minus Wk comma Vi divided by norm of Vi square, and then sum over I equal to 1 to k minus 1, and then inner product of Vi with Vj, right? Now because we already assumed that till k minus 1 this Vi Vj's are orthogonal, so this sum will survive only when I equal to j, right? By induction hypothesis. So when I equal to j, then this is non-zero, otherwise it is 0, right? So when I equal to j, what will have? So we will have Wk minus, inner product of Vj. Here I will have Wk comma or rather no, I think we cannot. Sorry. So you cannot take this sum outside because of this I is running also, right? So I rather write it down when I equal to j, what happened from here on. Okay, yeah, so I can't take it out. So when I equal to j, then only this. Okay, so how do I write down? So when I equal to j, then okay, this is there will be inner product here. Okay, I missed it. Okay, yeah, so inner product here. So when I equal to j, the inner product will survive, which is norm of Vj whole square, but when I not equal to j, it is 0, right? Because of the induction hypothesis. So when I equal to j, you will have this will be Wk comma Vj by norm of Vj's whole square, and this will be Vj, right? But Vj is nothing but norm of Vj square, so this gets cancelled, and you will have ended up with this. And this is true for all j equal to 1 to n, right? Up to k, whatever. Yeah. Yes. What and this is this, you give 0. So finally you got that this with the index hypothesis that till k minus 1 is 0, then vk is also index in a product 0 with all the vj's. That means vk will be also linearly independent, or rather orthogonal with all such vector, right? So that gives you the proof that this set w dash k is orthogonal. So thus w dash k is orthogonal. Okay, orthogonal. But you need to also prove that they are obviously also and hence linearly independent. Hence linearly independent, right? That we already proved. Orthogonal sets are always linearly independent. Orthogonal non-zero, obviously then nothing is 0 here. Okay. So one can ask why. Okay, so one thing I should say. How do you know that the vk is not 0, right? Till k minus 1 I assume that they are orthogonal, so then cannot be 0. 0 means they are linearly independent, right? So one can ask here, what if vk equal to 0? So that I should say, okay, so if is vk equal to 0, then what happened? Now if your vk will be 0, then you see that that the way we define vk, then wk will be nothing but sum of wk and vi with norm of vi square into vi, right? I equal to k, I equal to 1 to k minus 1. So what does that mean? That means wk actually belongs to the span of wk minus 1 dash. Okay, but by index hypothesis this is same as span of wk, and hence it's small wk, this small, okay, this small wk, this capital wk. So what does that mean? That means the small wk is linearly dependent, with the other w1, w2 and wk minus 1, which is a contradiction, because the originally we started that w1, wk is linearly independent, right? Which is a contradiction, which is a contradiction. Okay. So none of those vi's are 0, v1, v2, vk's are 0. Okay. And so non-zero orthogonal sets are linearly independent, that we already proved in last class. So what does that mean? That means the span of wk dash is always subset of span of wk. This is capital set. It's capital wk as a set. So that means elements are small w1, small w2, small wk, right? But see, it has k many linearly independent vectors. And also because wk dash also linearly independent, and it also has k many vectors. Again, so again, you see that this cardinality of these are same, and they have the same cardinality are same, and not only that, this wk dash also exactly same many linear vector. So what does that mean? That means they has to be same. So the subspace spanned by this equal to same as or rather subspace spanned by this, they are same. Okay. So this has to be seen, otherwise because this is a proper, if it is proper subspace, then number of linear independent vectors is less than ws, right? Because both are finite dimensional, right? But it's not the case. Okay, so here I am assuming, I mean, the finite dimensionality is needed. Okay, if it is not finite dimensional, then it can be the case that it is proper but same number of linearly independent vectors. Okay. So this is the actually proof that tells you that so this is true for any k, okay, and hence so this complete. Okay, so I think I should not say anything more. I think it is now clear that this is the proof of the fact that whenever you have a linearly independent subset of a inner product space, you can always convert it into a orthogonal set such a way that they generate the same vector space. This is the more important thing. They generate the same vector space. Okay. Okay. So now, what is the corollary of this fact? So the immediate corollary. So it is true for. So I see in the case in the process I did not mention that whether this is, for example, finite enough or not. But in general, so thus so you can write as a theorem that let V be a finite dimensional, or I should say non-zero because 0 is trivial case away. So for 0 is nothing is true. Okay, so non-zero finite dimensional inner product space then V has an orthogonal basis, because once you have orthogonal set, then you can quotient out by the norm. I mean, you can divide by norm to the vector of those vectors and it become orthonormal, right? Orthonormal basis. So maybe let me write down B, which is of the form say V1, V2, Vn, such that you can write down any vector such that for any vector V of V can be written as the inner product of V with Vi multiplied with I and I equal to 1 to n. Okay, and this is method also we discussed in last class, that for orthonormal set you can always write down this, right? Okay, so this is almost immediate to the fact that you can write down any orthonormal vector to orthonormal basis by this method. This is already proven in last lecture. Okay, and now the Gram-Schmidt process tells me that whenever you have a linear subset, you can convert into a orthogonal set. So in particular, I mean, if it is a finitely many elements are there in the orthogonal set. So in particular, when you have a finite vector space with a linearly independent basis, then you can convert the linearly independent basis to a orthogonal basis using the method whatever we just discussed called Gram-Schmidt method. Okay, where is the yeah, this Gram-Schmidt method, and then the resultant set becomes orthogonal subset, orthogonal basis, but that may not be orthonormal. So for that you just have to define every vector by its norm, and then that vector becomes the orthonormal basis. Okay, so now maybe I can give some example to clear it, and then maybe some more theorem can do it. Okay, so what will be the proper example for this? So let me maybe example number 1. So I will be equal to say R3. So let me take R3, and I am assuming a basis maybe say 1 1 0, and so I'm just choosing randomly. Yeah, so we check 1 into. So this linear number, obviously there is no problem, but is orthogonal. So 1 into 1, 1 into 0, 0. So no, this is not orthogonal. So this is a basis, obviously, because this is linear independent, right? Now question is that can you make it to a orthonormal basis of R2 from this? Okay, the answer is yes. So this is our my W1, W2 and W3, right, in that problem. And our V1 will be what? V1 will be W1, right? But what will be V2? So V2 will be W2 minus inner product of W2 comma V1 by norm of V1 whole square, okay, into V1, right? This is by the way we define it, okay? Now now what is okay, so let me, if I put W2 is 1, 0, 1. Now what is inner product of W2 with W1? So 1, 0, 1, and then comma V1 is in 1, 1, 0, inner product of these, and divided by norm of V1 square. So what is norm of V1 square means? So you can easily find out norm of V1 square is nothing but inner product of V1 into V1, which is nothing but inner product of W1 and W1, right? So this is W1 into W1, and this is nothing but so 1 into 1 is 1, 1 into 1 is 1, so 1 plus 1 is 2, and then 0 into 0 is 0, right? So this is 2. Now you see that this is same as for so this is norm of V1, so now W1, W3 also same, but norm of V2 is different probably, okay? So so this is okay. So norm of V1 is equal to this, and so you can write down this is 2 and times V1, so V1 is again W1, so it is 1, 1, 0, this vector. Now what is the inner product of this vector W2 with V1? So this is, if you take inner product, so you will have, so let me write down this properly. What is the inner product? So 1 into 1 is 1, 0 into 1 is 0, 1 into 0 is 0, so this is 1, so this is 1 half, and then you have 1, 1, 0, okay. Then what is the resultant vector? The resultant vector is nothing but so this is the first quadrant is half, I will have half, so you will have half, and then it is minus half and 0, so this is minus half, and third quadrant is 0 and then 1, so 1, right? Is that okay? So half minus half 0, okay? So this is the vector V2, okay? Is that fine? So let me check one more time. So this is inner product is 1 and 0 in 1, 0, okay? And this vector is 1 by half, and then you will have 1, 1, 0, which is W1 and V1 same. So you will have first quadrant 1 minus half equal to half, 0 minus half equal to minus half, 1 minus 0 will be 1, okay? That is fine. So I now got my V2. So I got my V2, which is nothing but half minus, right, minus half and 1, and then I can easily find out what is norm of V2 square, which is inner product of V2 with V2, and that gives you that half into half equal to 1 by 4 plus minus half into minus half into 1 by 4 plus 1 into 1 equal to 1, and which is nothing but 1 half plus 1, which is equal to 3 by 2, okay? So norm of V2 equal to 3 by 2, okay? And hence we can, so now so this is obviously not norm 1, so this the vector I am going to get V1 V3 are not orthonormal, they are only orthogonal, okay? So now how to find out V3? Now V3 will be equal to W3 minus W3 comma W1, and then sorry, other B1 I should say. B1 equal to W1, but let me write down by the method, and V1 square into V1 minus W3 comma V2 divided by norm of V2 square into V2, right? So now we need to calculate all the factors individually. Now let me calculate. So I already know what is V1 norm of V1 square and what is norm of V2 square. That we know. But these two quantities we need to calculate, this one and this one. Okay, these two quantities. Now let us calculate that. So what will be W3 in a product of V1? Okay. So W3 what? W3 is nothing but 0, 1, 1. And what is V1? V1 is W1, so it's 1, 1, 0, right? Is that okay? So let me check it again. Yeah, 0, 1, 1, 1, 1, 0. Okay. Now what will be the inner product here? Inner product will be 0 into 1 is 1, 0, 0, 1 into 1 is 1, 0. So this is 1. Inner product is 1. Now what will be W3 comma V2? So again 0, 1, 1. And what is W2? So V2 is half minus half 1. So let me write down here half minus half and 1. And what is the result? 0 into this equal to 0, 1 into 1 half minus half. And then this is plus 1, so this is plus 1, plus half. Okay. And done. So what will be W3? So W3 is nothing but, sorry, V3. So V3 is nothing but, and now use the formula W3 minus this, so W3 is 0, 1, 1 minus this quantity by norm of P1 square, which is 2. Okay, this is norm 2 vectors. Okay, but this was this different norm 3 by 2 vector. See, this is when you multiply this with half, so half into half will be 1 by 4, right? So 1 by 4, right? So so this is half 1 divided by norm, which is 2, and then we'll have V1. V1 is nothing but W1, so 1, 1, 0 divided by this one is half. And the norm, what is the norm here? Norm is 3 by 2. So 3 by 2. And then you have V2 is this vector, right? So this is half, comma minus half, and 1. Now the 2 get cancelled. You'll have 1 by 3. So you have 0. Okay, so first polynomial will be 0 minus half, and then minus 1 by 6. Second quadrant is 1 minus half, minus plus 1 by 6. Third coordinate is 1. This is 0, and this is 1 by 3, so minus 1 by 3. Okay, so now let me conclude. So this is minus half, and then minus 1 by 6, and that will give you minus 2 by 3, right? Because this is 1 half means 3 by 6, and 3 by 6 plus 1, 4 by 6 is 2 by 3. And we'll have so 1 half minus 1 by 6. Okay, so this is half. 1 minus half is half, so half plus 1 by 6 is what? Again 2 by 3, because again half means 3 by 6 and 1 4 by 6, so it's 2 by 3, and then we'll have 2 by 3, 1 minus 1, so nice vector. Okay, so we'll have a vector this. So finally, so this is my V3. So finally, what we'll have? We'll have this final, that maybe B dash, we'll have 1 1 0, and second one is half minus half 1, and third one is minus 2 by 3. Okay, so minus 2 by 3, 2 by 3, and 2 by 3. Okay, I am claiming that this is a orthogonal basis. So how to check this orthogonal? Orthogonal means inner product with any two defined will be 0, right? Now you can check it. You can check that why it's orthogonal. So for example, so this is my v1, v2, and v3. My inner product of v1 with v2. Yeah, so this is real vector space. So v1, v2, and v2, v1 are same. So you don't have to bother about that, right? So this is, you check that this is half and the minus half and 0. So this is 0, right? Similarly, in the product of v1 with v3, we'll have, see, minus 2 by third plus 2 by third and 0. So this is 0 again. And in a product of v2 and v3, and this is half into this. So this is minus 1 by 3. This into this minus 1 by 3. This into this is minus 1 by 3, and this into this is plus 2 by 3, and this is again 0. Okay, so that tells you that this is a orthogonal set, and hence this is orthogonal basis because these are linearly independent, right? So now how to check what is that then orthonormal? So I just want to find out the orthonormal basis for this. How to find out that thing? So this is also simple. And now what do you do? So you have to now divide by the norm, and then you have the orthonormal things. Now the norm also you already find. So thus the orthonormal basis obtaining 10 from this beta with this Gram-Schmidt method. Obviously, there might be, see, if you don't apply Gram-Schmidt method, you may have, if you can start with another vectors, like for example, you can, instead of choosing v1 equal w1, you can choose v1 equal w2 and do the process. Still you will have your orthonormal basis, but that will be different basis. Okay, so with this Gram-Schmidt method, is given by, so what was the original one? So this divided by the norm. So norm is what? So norm of this equal to root 2, right? Because 2 is the norm square. So norm of this root 2. So this will be 1 by root 2 into 1 1 0, and hence this norm will be 1 right now. Okay. Similarly, the second one was what? Second one, the norm was 3 by 2, right? Where is b2? Norm of b2 square is 3 by 2, and hence norm of b2 equal to root over 3 by 2. So this will be root over 2 by 3 because you are now dividing. And then what was the vector? Vector is half minus half and 1. And the last one is what? So last one norm is what? So let me find out the norm here. Okay, so this is v1, v2. Yeah, so now v3 is this vector. What is the norm of this vector? This is v3. Okay, that we did not check it here. Now we can check it also here. The norm of v3 is what? Root over of, so minus 2 by 3 into minus 2 by 3, so that will give you plus 4 by 9, minus 2 by 3 into by 3 again, sorry, plus is 4 by 9, and again it is 24 by 9, and hence this is 4 by 3, Okay, so hence the norm is 2 over root 3, right? Is that okay? Yeah, so thus this answer will be root 3 by 2 times minus 2 by 3, 2 by 3, 2 by 3. And you can get cancelled 2 also. So root 3 into minus 1 by 3. Yeah, so that will be, so this is the norm, this is the orthonormal basis that coming from that given basis with respect to this method. Okay. Okay, so this is one example, proper example I gave. I just want to discuss one more example, which is also important example, and that gives us something called legendary polynomial. So what are the legendary polynomials? So let me just, okay, so example number 2. So you start with a space of polynomials over real numbers, okay, and the inner product is what? Inner product is here. You take f and g, and you define minus 1 to 1 f of x g of x dx. Okay, this is my inner product, and then you take the subspace. So you take the subspace W, which is space, rather, okay, I should say it as a name. So you take P to R. So all the polynomials of degree less than equal to n, and this is generated by the vector 1 x and x square. Space of polynomials whose degree is less than equal to 2, right? Now the natural question is that so this is obviously a linear set, but this is not orthogonal. Okay, with respect to this inner product. Okay, or rather the norm coming from the inner product. Okay. Now, how do you find out a basis which is orthogonal from this? Okay, and then once you find out the orthogonal thing, then our question is that how do you find out the orthogonal basis? So let me first find out the orthogonal basis, and that is called legendary polynomial. So what are the legendary polynomials? So let me just define it here. It's called legendary polynomial. Polynomials are the basis, orthogonal basis of the standard basis of PR. So that is 1x, x square, and so on. And with respect to the Gram-Schmidt method, okay, are the orthogonal basis of orthogonal basis of this b with respect to the Gram-Schmidt method. Okay, with respect to this Gram-Schmidt. I just wrote GS, but you should write down full name, Gram-Schmidt method. Okay, because I wrote many times. Okay. Now let me find out first 3 that will be orthogonal basis of this, and that will be the first 3 this legendary polynomials, like polynomials 1, 2, and 3. Okay. Now how do you find out the first 3? Again, the method is same. So you choose your v1 equal to so w1 will be equal to 1. Okay, this is w1, w3, right? Now and then check what is the norm of v1. Okay, the norm of v1 square is minus 1 to 1, and the 1 into 1 was 1 times dx, right? This is what this is. 1 into 1 means 1, that dx. What does that mean? That means x, right? So this is integral over x minus 1 to 1, which is number 2, right? So norm of v1 is 2, which is not norm 1 vector, obviously. So now v2 again, you find out this is nothing but w2 minus w2 v1 divided by norm of v1 square into v1, right? What was w? W was x, and then this is inner product with x with v1 1, and then this is 2 into v1 is 1, right? Now what is the inner product of v1 into x? Now check that. Okay, so now, so what is this x comma 1? This is minus 1 to 1 x times 1 into dx, but this is nothing but x squared by 2 minus 1 to 1, so this is 0 actually. So what does that mean? That this portion 0, so you have x. Okay, so the second vector is also x, and once you have second thing, so you can ask what about v3. So first original polynomial is same as that original basis. Now what is v3? Now there will be a twist here, so v3 will be w3 minus w3 of v1 with the product of v1 square, now v1 square into v1 minus w3 into v2 divided by norm of v2 square into v2, right? Now now you find out this homework. This is your homework, and do that. So you will find out that this is actually x square minus 1 by 3. It's not exactly x square. So the new basis, orthogonal basis, will be 1x square minus 1 by 3, and that will be, so this is the basis of consisting of legendary polynomials. Okay, and you can continue the process obviously, but this is not orthonormal. This is orthogonal only because the norm of everything is different. Now it is orthogonal, orthogonal basis of P2R. Now again I am giving you homework to find out the orthonormal basis. Again, another homework, find out that if you want to find out orthonormal, then you divide the norm of 1, which is 2. Okay, norm of 1 square is norm of 1 whole square equal to 2, so norm of 1 will be 2. Similarly with norm of x and norm of these vectors, and then you find out the orthogonal basis of P2R. Okay. Okay, maybe I will stop here, and there are many applications maybe I can discuss later. Okay.